My name is Louis Fest. I'm a graduate student at California State University, Fullerton, and Starrett has been kind enough today to allow me to test out a custom-made profile sting meant for use in a wind tunnel on the FMS 1000. So the main purpose of this test is essentially to verify the rigidity of this sting, which is going to be suspended in a wind tunnel like so. Our main purpose of application for this is use with ground vehicle aerodynamics. So we're looking at potential failure points in two locations today. One at the center of pressure of the sting, which is the current configuration you see. The second will be at a point about 3 inches off the end of the sting to simulate a model. And our goal today is to see where they fail. All right, here we go. I hear it. There it is. So as we saw doing the tests on the tensile machine right behind me, we had two forms of failure occurring on each of the sting balances, of which we tested 3. That first form of failure was compressive buckling, which you can see here in figure 411, where you start to have this sort of compression effect along the trailing edge, which is where we expected to see our maximum compressive forces acting. And once that compressive buckling occurs, we then have a subsequent leading edge tearing where the layers begin to separate at the front right above the actual fixture point. Of course, this is all in an effort to understand what the actual experienced forces are. So starting off with our first specimen here, which was the 0.8 millimeter wall thickness specimen, we saw that there was a single failure point in which the compressive failure and tensile failure happened simultaneously. Once we reach that rupture point around 0.27 megapascals, we immediately drop off, and the material does attempt to reload itself as the load distributes to other layers, but it never fully recovers, and at that point we call the test a success or failure. The immediate subsequent test, which was on a 1 millimeter specimen, saw the most failure types. Here we see a sort of elastic region as we approach that compressive buckling point. Once we reach that failure point, we have sort of a popping that disengages our specimen from the machine ever so briefly until it re-engages and leads to our next failure, which was the outer leading edge tearing point. And again, once we get that first tear, we disengage briefly until we approach that final tearing point there, which then after failure drops us off, and we again have re-engagement attempted, but at that point our material is deemed a failure. And finally, our strongest material, which was a solid leading edge on that 3D printed sting, we see again a much broader elastic region followed by a compressive failure point and an immediate leading edge failure point and no recovery at all. So looking at all 3 of these side by side, we were thankfully able to see that there was a appropriate material trend, and that as we increase the wall thickness of our prints, we start to see that we're able to sustain greater forces. Each of them behave similarly in that they approach a buckling failure point immediately preceding a leading edge tear point, and there is no recovery at all. Once we reach that, the parts will be deemed a failure. They need to be replaced. Here, our maximum achieved stress was about 0.57 megapascals, which is well above the threshold of what we anticipate seeing in a wind tunnel. Even though the 1.3 millimeter wall worked the most effectively, we are going to be moving forward with the 1 millimeter wall specimen. Because of the visible signs of fracture, we want to be able to discern imminent failure before we lose a component or any material inside of each sting.